Welcome back, everyone. This is our very first session of 2026. Wish you a very happy new year. Hope you had a fun holidays. And yeah, I'm really excited to introduce Zhihan, who is a first year PhD at Cornell. And yeah, he'll be presenting our paper, Esoteric Language Model. So yeah, Zhihan, feel free to take over.
All right. Thanks, Shubham, for the introduction. So, yeah, as you said, I'm a CS PhD student currently at Cornell, advised by Professor John Sixton, and my research focuses on generative models. Today, I'm very excited to discuss with you our latest paper, Esoteric Language Models. This is a project that was co-led by Shubham and myself, and it is a collaboration between Cornell, the Institute of Foundation Models, and NVIDIA Research. In this paper, we introduce a new family of language models that fuses autoregressive and mass diffusion language models. Importantly, this is the first paper that introduces exact KV caching and exact likelihood computation for mass diffusion models. So here is a brief overview of the agenda today. I'll begin with some relevant background, comparing and contrasting autoregressive and mass diffusion models, which I believe many of you might be familiar with already. Then I will describe some important limitations of current state-of-the-art mass diffusion models that we focus on tackling in this paper. Our solution to these limitations are our key contributions. In particular, we're the first to unlock exact KV caching for MDMs without sacrificing parallel generation over the full sequence length. We close the perplexity and generation quality gap between AR and MDMs. And additionally, we're also the first to unlock tractable likelihood estimation and exact likelihood computation for MDMs, which we believe could prove to be very useful for the RL fine-tuning of MDMs. Finally, we'll conclude and have a Q&A session, but of course, I'm happy to answer questions throughout the talk as well. So let's get started with background. In standard autoregressive text generation, text is generated one token at a time from left to right. This means that the number of steps it takes to generate a piece of text is equal to the number of tokens in the sequence. Since each token only depends on other token on its left, autoregressive models are typically parameterized by a transformer with causal attention. For mass diffusion text generation, things work a bit differently. We start off with a sequence of mass tokens. Then at each step in the generation process, we unmask one or more tokens into clean tokens. Until the entire sequence is clean. This means that the number of steps it takes to generate a piece of text could be smaller than the number of tokens in that text, which is very interesting from an inference efficiency standpoint. And since each new token depends on previously generated clean tokens in both its left and right context, mass diffusion models are typically parameterized by a transformer with bidirectional attention. Now we have a good intuition on what autoregressive and mass diffusion models are. Let's dive into a state-of-the-art mass diffusion model, MDLM, and see how it is trained and sampled from. In MDLM training, we sample a clean sequence from the training set. We randomly mask out some clean tokens to obtain a noisy sequence ZT, also known as a noisy latent. Note that this masking process is parameterized by alpha sub t, which represents the probability that a token remains to be clean after random masking. We forward ZT through the bidirectional transformer to obtain logits over the mass positions in Z sub t. So here the superscript L denotes the position in the sequence. So here we have 2, 4, and 5, which corresponds to the mask positions 2, 4, and 5. And finally, we compare the logits with the ground truth clean token and compute the mass diffusion elbow as the training objective. So this objective is a sum of the cross-entropy losses over the masked positions in ZT weighted by some scalar. There's also an expectation in front with respect to the masking process, which we approximate with a single Monte Carlo sample, as shown in the bottom of the slide. So for those who might be unfamiliar with what elbow means, here's a quick note. So in standard maximum likelihood training, we're interested in maximizing the log likelihood on the left. However, for many latent variable models, including diffusion models, the log likelihood is intractable. And therefore, we choose to instead maximize a lower bound that's tractable, which we call the elbow or the evidence lower bound. During training, because we're running gradient descent, we apply negative sign on both sides of this inequality to turn this maximization problem into a minimization problem. And when reporting perplexity during evaluation, we use the exponentiated lens normalized elbow, which is an upper bound on the true perplexity. So after we train the MDLM in this way, we can now sample from the model. So the MDLM sampling, of course, happens in many steps, but let's first look at a single sampling step in this generation process, in which we're trying to go from ZT to ZS, where ZS is a less noisy version of ZT. So more concretely, it should have more clean tokens than ZT. And just a side note here, so we might use the word inference and sampling interchangeably throughout this talk. So in this single step of sampling, we first forward ZT through the bidirectional transformer to obtain clean predictions for every position. If a position is already clean in ZT, we directly copy that token to ZS, as shown on the left, where we say keep unmasked inputs. If a position is masked in ZT, we retain the prediction of the transformer with some probability. And doing this procedure repeatedly would let us go from Z1, which contains only masked tokens, to X, which contains only clean tokens. Now let's get into some key limitations of current state-of-the-art MDMs like MDLM. So one of the most important limitation is that MDLM lacks exact KV caching. And here's an illustration of how autoregressive inference works. So let's say you have a BOS token and you pass that into the model, which gives you, let's say, token A. You pass A back into the model to get token B. You pass B in to get C. And importantly, when you pass C into the model, because of the use of causal attention, forwarding C does not affect the representations of previous decoded tokens, which means that the KV values of previous tokens can be cached and don't need to be recomputed in subsequent decoding steps. This is known.
Do you mind using a pointer so that it's easier to follow? Like I was sort of a bit lost.
Can you see the?
Let's just switch to the pointer that comes with. Oh wait, you're not using Google Slides, right?
I am.
Oh, so yeah, okay, at the bottom left, there should be a pointer, like so that's more visible.
I see.
If you navigate to bottom left, I don't know, hover over.
Let me see this. Yeah. Can you still see my slides all right?
Okay, to turn on laser pointer, yeah. No, the second option, laser pointer. Yes. All right, much better.
All right. Thanks. So when you forward token C into the transformer, the KV values of previous tokens can be cached and don't need to be recomputed in subsequent decoding steps. And this is known as KV caching, which is a crucial inference time optimization technique for autoregressive models. In fact, without KV caching, autoregressive inference has a time complexity that's quadratic in sequence length, but with KV caching, this drops down to only linear in sequence length. However, bidirectional attention in MDLM prevents KV caching. Again, let's look at an example. So here we're trying to generate a sequence of length 6. So we're inputting a sequence of 6 mask tokens into the bidirectional transformer. And let's say position 2 and 4 get selected for denoising, and they're denoised into, let's say, token B and D. And then we pass token B and D back into the model, along with the remaining mask tokens. And this time, let's say position 1 and 6 gets denoised into A and F. In the third step, when A and F are passed back into the model, notice how the KV values for token B and D are now changed because of bidirectional attention. And more generally for MDLM, when a new token is unmasked, the KV values of all positions have to be recomputed, which makes each inference step in MDLM much more computationally expensive than a standard autoregressive model. The second major limitation is that MDLM cannot tractably estimate the likelihood of a sequence. So in your typical RL for LLM reasoning setup, you pass the prompt into an LLM, which generates some chain of thought trajectories. So these are the sequence of interest here. And a common way to score these trajectories is through verifiable reward. So for example, you get a +1 for getting the question correct and -1 for getting the question wrong. And what policy gradient RL algorithms do is that they try to increase the likelihood of chain of thought trajectories with positive normalized reward. However, since the likelihood is intractable for MDLM as it is a diffusion model, we resort to the Nelbo, which is a bound on the likelihood. There are two main options for the Nelbo. One option is the MDLM Nelbo, which is also the MDLM training objective that we saw earlier. It is an expectation of a weighted cross-entropy loss over the noisy latence derived from X. To accurately approximate this expectation, though, it requires a number of samples of ZT that scales linearly with the sequence length. Additionally, each sample of ZT requires a separate forward pass. These two things combined means that accurately estimating the MDLM Nelbo is highly computationally expensive. While this can be done for a single X, this is pretty intractable for policy gradients.rl, in which likelihood computation is a subroutine that needs to be called repeatedly. Fortunately, besides the MDLM Nelbo, there's a second option called the any-order autoregressive Nelbo. The RAD paper showed that this is equivalent to the MDLM Nelbo under the linear noise schedule. And it is an expectation of the autoregressive likelihood under a specific ordering of data over all possible orderings. And to accurately estimate this expectation, we can get away with a single sample of a sigma, which is the ordering, or maybe more rigorously, a constant or O1 samples of sigma. And here's the intuition. So the MDLM Nelbo above is derived under the continuous time formulation that corresponds to the limit of having infinitely many diffusion steps or diffusion sampling steps. And when the number of sampling steps is taken to infinity, at each sampling step, at most one token is denoised. So when you look at this entire diffusion trajectory this way, you soon realize that it can be viewed as autoregressive generation by some particular ordering. So therefore, the AR likelihood inside the expectation essentially compresses and accounts for an entire diffusion trajectory which contains L noisy latents.
Sorry, what's
Yeah.
the sigma? What's the sigma here?
So sigma is represents an ordering over the.
Okay, so it's a random order. And how
Yeah.
does this compare to your standard AR models? Like
Right.
the equation that I say, yeah.
Yeah. So in your standard AR model, your ordering would be like the standard natural left to right ordering, like 1, 2, 3, 4 up to L, which is the sequence
Okay.
length.
Yeah.
Yeah.
Okay. Okay. Oh, and one small thing. I think for some reason after you turn on the laser pointer, the screen size reduced. I don't know if it's for everybody or it's
Is
just
it a bit
for me.
is it a bit like low res now?
Um,
Is it better now?
yes, yes, yes. Yeah, because we were recording it, so that's why I thought
Okay.
I should bring it up. Right.
Yeah.
Right. Cool.
Thanks. Fortunately, we'll see that for Eso-LMs, this will be reduced to just a single forward pass, enabling tractable likelihood estimation. So just to recap, we described two limitations of MDLM, one being that the inference lacks KV caching, and the other being that it cannot tractably estimate likelihood of a sequence. So let's see how Eso-LMs tackle this first limitation. So earlier we covered how training for MDLM works. For esoteric language models, we keep everything the same, except that the transformer is no longer bidirectional. Instead the transformer, we shuffle the noisy sequence such that the clean tokens precede the mask tokens. We also perform random shuffling within the clean tokens and within the mask tokens. And this is inspired by mass diffusion models' connection to any order autoregressive models. More specifically, we assume that the clean tokens were generated in some random order, and that the mask tokens are also to be denoised or to be unmasked in some random order. Yeah, and on top of this shuffled sequence, we apply causal attention. So finally, it's worth noting that our method relies entirely on rotary positional embeddings, just like the state-of-the-art autoregressive models and MDLM, as opposed to more complicated solutions introduced in prior work on any order autoregressive models.
I have a question.
Yes.
Can you please explain causal attention and also what you mean by noisy data?
Sure. So causal attention, it means that like in your transformer, you are only attending to tokens on the left. So for example, here, this token only looks at other tokens on its left. So that's what we mean by causal attention here. And the noisy sequence, it just means that, so we have a clean sequence that's sampled from the data set. So this could represent like a sentence, for example, and you basically randomly mask out some clean tokens and convert them into mask tokens as shown in gray. So this is what we mean by noisy sequence.
Okay, thank you.
Yeah. So this form of training that we saw earlier actually unlocks KV caching during Eso-LM inference. So as with MDLM inference, tokens are unmasked in random order across a sequence. Let's say that in the first step, positions 3 and 2 are selected for unmasking, and they get unmasked into token C and B. In the second step, we pass C and B along with the masked tokens. We pass C and B along with the masked tokens carrying new positions to denoise into the transformer. And let's say that these masked tokens gets denoised into A and H. In the third step, we pass A and H generated in the previous step back into the transformer, along with additional masked tokens carrying positions to denoise. But now notice that the KV values for C and B can be cached due to the use of causal attention. And so on and so forth until the entire sequence has been filled.
A quick question on that item. So you're able to reuse the KV cache once the entire contiguous like previous sequence has been generated. But if, let's say like for example at step 3, you had A and C unmasked, but you didn't have B. You wouldn't be able to would you be able to use a KV cache in that case, or would you need to wait until B was unmasked?
Sorry, could you repeat that question?
I'm just sorry. I'm just trying to understand the mechanism for the KV cache here. So do you need to have the entire contiguous sequence unmasked, or can you have like for example like at step 4 where you have C, B, A, H unmasked?
That's a great question. Yeah, so I think like I chose B and C just like it was pretty random. I think like I could have chosen like 2 tokens that are like far apart. So yeah, to answer your question, like basically we don't have to cache like tokens that are like contiguous in the natural order. It's just that whatever that was generated in the previous steps, we're able to cache those. Yeah.
Gotcha. So you can cache regardless of order as long as they were previously generated.
Yes.
Cool. Thank you.
Yep. So to showcase the inference efficiency benefit of KV caching, we plot the speed quality trade-off on unconditional generation of Eso-LM against the baselines. So all the models here are GPT-2 sized, 110 million or 0.1 billion parameter models trained on open web text. And for diffusion models, the trade-off in speed and quality is achieved by varying the number of diffusion sampling steps. So on the horizontal axis, we have the mean sampling duration it takes to generate a batch of 512 unconditional samples of lengths 1024. So the x-axis, so the mean sampling duration per batch is a measure of throughput, and in this case, it's lower the better. On the vertical axis, we have generation quality. So here we have Gen PPL, the lower the better, and here we have MOLV, the higher the better. So for the plot on the left, we want points to be closer to the bottom left, whereas in the plot on the right, we want points to be closer to the top left. So here we have the black star represents autoregressive models. We see that it achieves a good quality in a reasonable sampling time budget, but it does not offer any speed quality trade-off because it's just generating 1 token at a time. MDLM achieves a speed quality trade-off, as we can see in the purple curves. But it takes way too long to generate samples of decent quality. And this is especially true because notice how the horizontal axis is actually log scaled. And this is primarily due to the lack of KV caching. And on the other hand, we have Eso-LM, which achieves a much better generation quality than MDLM at low sampling time budgets. And this is because as a specific sampling time budget, Eso-LM can perform more denoising steps with KV caching enabled. Well, this is seems nice, but there is a natural question. So we see that there is still a gap between Eso-LM and AR. And since Eso-LM and AR share a very similar inference scheme with KV caching enabled, there's a natural question that can we interpolate between these two kinds of generation with Eso-LM being a kind of mass diffusion model? And if we can close this gap, that would be great. So this leads to our second contribution, closing the perplexity and generation quality gap between AR and MDMs. So to achieve this, we introduce Eso-LMs, a family of models fusing autoregressive and mass
Hi,
diffusion.
before we move on, I have a question about the generation scheme. So am I understanding correctly that you train with a bidirectional attention, and then during inference you do causal attention, but with a shuffled position? Is that right?
So the second part is right, but we actually train using causal.
You also train.
Yes.
Okay, you also train with causal attention.
Yeah, I think this is actually a key differentiating factor with between our work and some of the other works that explores KV caching, because in our case, like our models are trained to use causal attention. So during inference, we actually have exact KV caching, whereas other methods rely on approximations. So they train on bidirectional attention, but during inference, they use some trick to do caching.
Okay, thank you. Very cool.
Yeah, thanks. So we have Eso-LMs, a family of models that fuses autoregressive and mass diffusion models. And in this family of models, we first generate a proportion of the tokens by diffusion. So this proportion is a hyperparameter, alpha 0. Then we fill out the remaining mass positions sequentially, one at a time from left to right. So we fill in these mass positions one at a time from left to right. And note that the sequential phase is a bit different from standard autoregressive generation because each newly generated token needs to attend to both left and right contexts. So for example, when you're generating the token flat, the model needs to know that Earth is what's coming up on its right. And when generating the token society, the model needs to know that the phrase flat Earth is on its left. And when alpha 0 is equal to 1, so we have all tokens being generated by diffusion. So this is actually the singular Eso-LM that we introduced earlier in the talk. And when alpha 0 is 0, all tokens would be generated sequentially. And this would mimic a standard autoregressive model. So by varying alpha 0, we achieve a fine-grained interpolation between autoregressive and mass diffusion models. So to make things more concrete, let's look at how things are done in more detail. So the diffusion phase is more parallelizable and controllable, as we can unmask more than one token per step over all positions in the sequence. However, as we see earlier in the speed quality trade-off curve, diffusion leads to somewhat lower generation quality, which also agrees with the literature. The sequential phase is less parallelizable, but AR generation leads to better generation quality. So Eso-LMs combine diffusion and autoregressive inference into a new kind of hybrid inference that share a single unified KV cache. So as we can see, after the diffusion phase is finished, we can perform a sequential phase simply by passing in, we can perform the sequential phase simply by passing in mask tokens, carrying the remaining positions in sequential order. So for example, here we have the 5th position being masked. So we pass in a mask token carrying the position 5, which gets unmasked into token E. And here the 7th token is unmasked. So we pass in a mask token carrying position 7, which gets unmasked to token G. And notice that during this phase, we are working on the mask tokens one at a time from left to right. Again, I think it's worth emphasizing that the sequential phase is not standard autoregressive generation. There are two differences. So first is that we used mask token placeholders like these to tell the model which position to denoise. And the second key difference is that when denoising, the model leverages both left and right context. So for example, when generating E, all of A, B, C, D, F, and H, which were previously generated, are all in the left context of E, which it can attend to by causal attention. So in our paper, we derived a principled Nelbo, a principal training objective for this hybrid generative model that neatly decomposes into an AR component and a diffusion component, corresponding to the two phases of generation we discussed just now. So importantly, the AR model and the diffusion model share the same transformer parameters and simply use different attention masks during training. So to see how this works, let's consider a batch of 4 examples here. We evaluate the AR component on half of the batch and the diffusion component on the remaining half of the batch. So similar to what we saw earlier in the talk, for the diffusion component, we shuffle the clean and mask tokens and just apply causal attention. Things get a bit more involved for the AR component. So during generation, the sequential phase fills out mask tokens one at a time from left to right. But this causes an issue during training. For example, when you're predicting the third token, this requires the second token to be clean, which is a dilemma. And more generally, predicting a mask token requires all mask tokens on its left to be clean. So to resolve this dilemma, we concatenate the fully clean sequence along with the partially masked sequence and redirect the attention mechanism so that the third token now attends to the second position in the fully clean sequence, which is clean. So this resolves this dilemma. Unfortunately, doubling the sequence length always come at a cost, so this usually leads to slower training. But fortunately, due to the sparsity of the attention mechanism and the fact that we're only doubling the sequence length for half of the batch used to compute the AR component, Eso-LMs have a comparable training time compared to MDLM and are much faster to train than block diffusion or BD3LMs. So now let's look at the speed quality Pareto frontier again. By varying alpha 0, basically the proportion of tokens modeled or generated by diffusion, we can close the gap in generation quality and achieve a state-of-the-art Pareto frontier. There is a bit of a sharp drop for GenPPL, but the Pareto frontier for MOLV looks much smoother. And one might consider this comparison to be a bit unfair because the green curve here is made up of 4 Eso-LMs, each trained with a different alpha 0, whereas the MDLM curve, for example, is made up of just one single trained model. So to address this question, we train a single Eso-LM in full diffusion mode by setting alpha 0 equal to 1 during training. And so during inference, we vary alpha 0. So now we see that the Pareto frontier for this Eso-LM trained in full diffusion mode, we see that it's competitive compared to the frontier obtained by the 4 Eso-LM models trained using different alpha zeros. And this shows that Eso-LMs trained for diffusion only can flexibly adapt to a diverse set of denoising schedules. Okay, so finally, let's get to the third key contribution of our work, unlocking tractable likelihood estimation and exact likelihood computation for MDMs. So let's look at tractable likelihood estimation first. So earlier, we saw this slide earlier. We discussed one limitation of MDLM, which is that it cannot tractably estimate likelihood of a sequence. More specifically, we discussed two knowable options here and concluded that for MDLM, both options require a number of forward passes that's proportional to the sequence length. But we also said that the second option requires only one single forward pass for Eso-LMs. So let's see how this works using a concrete example. So suppose we have a token sequence and we want to compute the likelihood under some specific ordering. So in this case, we want the yellow token to come first, the green token to come second, the red token to come third, and the blue token to come last. And first, we shuffle the clean sequence in the desired ordering and also create a fully masked sequence with the matching ordering. The first term here is an unconditional probability of observing the yellow token in position 4. So the masked token carrying position 4 only needs to attend to itself, as there are no conditional information. The second term is the conditional probability of observing the green token in position 2, given that the yellow token is in position 4. So here, the masked token carrying position 2 attends to itself and the clean yellow token. The third term is the conditional probability of observing the red token in position 1, given that the yellow token is in position 4 and the green token is in position 2. So the masked token carrying position 1 attends to itself, the yellow clean token, and the green clean token. And things work similarly for the last term here. And one technicality is that the clean tokens, as we can see in these gray arrows that's barely visible, they also attend to each other causally to simulate a clean left context under this specified ordering. We have more details on this technicality in our paper. So this single pass likelihood estimation technique we introduce here has been cited and used in this paper, D2, Improved Techniques for Training Reasoning Diffusion Language Models. So we have a plot here. The task is to increase the toxicity of unconditional generation with RL training. So when they fine-tune Eso-LMs with our proposed single pass likelihood estimator versus an estimator introduced in prior work, we see that our estimator leads to a noticeable increase in toxicity, as shown in the solid orange curve here, whereas the previous estimator does not have this benefit, as shown by the solid blue curve at the bottom. So now let's look at exact likelihood computation. So previously, we have discussed that the any ordered elbow and the fact that for a single sigma, evaluating the AR likelihood inside the expectation requires only a single forward pass for Eso-LMs. And in our paper, we derived an importance weighted version of this any ordered elbow. And this bound is an expectation over k orderings. And crucially, we showed that this bound converges to the exact negative log likelihood as k approaches infinity. And so this is the first formula for exact likelihood of mass diffusion models, which we believe is quite significant. And while this bound also applies to MDLMs theoretically, it is computationally intractable. But for Eso-LMs, evaluating this bound only requires k forward passes, as there are k orderings under the expectation. So we now compare the likelihood of Eso-LMs against autoregressive models and MDLM. So we have two data sets here. We have LM1B and Open Web Text. In LM1B, the sequence length is somewhat shorter than Open Web Text. And on both plots, on the vertical axis, we have validation perplexity. The lower the better. On both data sets, we see that autoregressive models achieve a better perplexity than MDLM. And Eso-LMs enable fine-grained interpolation between autoregressive and mass diffusion perplexities by adjusting the alpha zero used for training. So a higher alpha zero means that more tokens are modeled by diffusion. So using the blue bars, we report perplexities computed from the mass diffusion elbow, which is an upper bound on the true perplexity. And using the yellow bands shown here, we report the exact perplexities computed from exact likelihoods, which are obtained from the importance weighted bound formula discussed on the last slide.
One question here. On this slide, we do see regression against the standard MD-LM for perplexity. Why do you think that is, particularly at where an alpha equals 1, where it's all diffusion?
That's a great question. One important distinction that we made in the paper is that so perplexity represents sort of your generation quality at an infinite number of sampling steps. But this is not very realistic. So during sampling, we see that with KV caching, Eso-LM can actually generate better samples in a given sampling time budget. But just to focus on perplexity, the reason why Eso-LM achieves worse perplexity than MDLM at the full diffusion mode is because this one is essentially just MDLM with sparser attention. So remember that during training, we basically switch from the bidirectional attention used in MDLM to causal attention. So that's basically you're cutting off a lot of attention connections. So naturally that leads to a slightly worse modeling ability, which is shown by the worse validation perplexity.
That makes sense. Thank you.
Yeah. Thanks for the question. So that pretty much concludes my talk today. So in summary, we are the first to unlock exact KV caching for MDMs without sacrificing parallel generation over the full sequence length. We close the perplexity and generation quality gap between AR and MDMs by interpolating between these two paradigms. And finally, we unlock tractable likelihood estimation and exact likelihood computation for MDMs, which we believe could prove useful for RL fine-tuning of MDMs. And for future work, we're really excited to see how Eso-LMs performance scale with model size and whether it can perform reasoning or maybe other tasks more effectively than existing models. Yeah, it's been a pleasure to share this piece of research today, and please feel free to ask more questions in the Q&A session.
Yeah, Zhihan, so it seems like there are some questions in the chat. Do you mind just going addressing them? Or?
Yeah, let me look at the chat.
So yeah, basically, yeah, if you could explain people how alpha naught is chosen and how we choose the denoising schedule and all those things. Yeah, I think it'll be helpful. So
I see. Okay, I'm sorry. I was just taking a moment to check. Yeah, so let me try to go back to the slide. Yeah, so basically the motivation of trying to interpolate between these two approaches is that as we saw in the speed quality Pareto frontier earlier in the talk, we see that there is a gap between Eso-LM and autoregressive models in terms of their generation quality. And so because of this, we basically introduced this knob alpha 0 that controls what proportion of tokens are modeled by diffusion or modeled sequentially. So this is a choice that we have to select at training time. And ideally during inference time, you also use the same alpha 0 during sampling. So you would first do diffusion to fill up a certain proportion of the tokens, and then you fill out the remaining mass positions one at a time from left to right. But things get a bit more nuanced because as we explore in this experiment, basically in the purple curve, we train a single MDLM with alpha 0 equal to 1. So this is a full diffusion Eso-LM. And during sampling, we tried using alpha 0 that's other than 1, right? So we used 1, but also 0 0.5, 0 0.25, and so on. And we see that the Pareto frontier obtained by doing so, by having this training and sampling mismatch, is actually quite small. So the purple curve almost matches the green curve, which is the green curve consists of 4 Eso-LMs trained for separate alpha zeros. So this just means that it seems like Eso-LM is very flexible in terms of its sampling time schedule.
yeah, so any other questions or?
Yeah, I have a couple more. One, I just want to say this is really great work. Thank you for presenting this. This is really a cool idea. It also kind of reminded me of a paper I saw out from UCSD called D-Flash. I'll link it in the chat. A very similar idea. They're essentially using diffusion models as in like speculative decoding. So using diffusion models as a first pass, like a student model. And then they're using an autoregressive model to essentially fill in the rest of the tokens as like a teacher model. I would say that the key difference between DFlash and Eso-LMs, from what I can understand, is that Eso-LMs use the same transformer weights to train both autoregressive and diffusion, whereas DFlash is using like a separate model, which I think is an advantage for Eso-LMs. I did want to ask, kind of along those lines, though, given that a lot of the work is looking at this speed quality Pareto frontier, have you investigated anything in the direction of maybe the model learning itself when it can fall back on diffusion generation versus autoregression, and we can learn on its own over time? These samples might be easier to predict with diffusion, and these samples might be harder to predict diffusion, so it can learn on its own rather than the user setting the alpha parameter. Does that question make sense?
Yeah, no, I think that's a great question. Yes, we haven't done any such study, but I think there's a lot of value into looking into this. For example, so what you're saying is there could be certain clusters of token that can be predicted in parallel without much drop in sample quality, because imagine this, right? Let's say you're predicting two consecutive words. Let's say you have two blanks that you want to fill, and two candidates that can go there is something like an apple or a banana. But if your model assigns high probability to A and N for the first blank and apple and banana for the second blank. So when you're drawing these tokens in parallel, what happens is you may end up with mismatched pairs where you will end up sampling like and banana, which is incorrect, right? So this particular example says that maybe there are certain words that cannot be predicted in parallel, but you can also have a group of, let's say in English language, there are a group of tokens that always appear together, but those ones can be predicted in parallel. So yeah, I mean, I think one should definitely look into it, and I'm pretty sure that you can come up with interesting ways where, or you'll make interesting observations where you'll find certain clusters of tokens can be predicted in parallel without any drop in accuracy, but there would be certain tokens where predicting them in parallel would lead to a significant drop in accuracy, such as the example that I just shared before. So,
Right.
yeah.
Like I think like for math, oftentimes if you have the left-hand side of the equation, like a number might be split up into multiple tokens, but because there's only one finite number that could be predicted,
Yeah.
like you can predict them both in parallel, or maybe uncommon words that get split into tokens, like maybe Google got split into like GO and then OGLE. I think there are like maybe some like a lot of like low hanging fruit where the model could very easily learn, okay, these tokens are typically going to go together. So I think that could be an interesting direction.
No, yeah, for sure. I think confidence-based unmasking, sort of tries to do that, where you only unmask, like when you do confidence-based unmasking, you decode tokens that the model is really certain about, and in doing so, you may end up, in many cases, you end up predicting tokens um, uh, that I don't know that should be decoded that can be decoded in parallel without much drop in accuracy. So, but yeah, that aside, I don't think people have looked into it. But yes, that's something worth thinking about. Yeah. Uh, yeah. Okay. So, Toby, like, do you have another question, or I see you raise your hand.
Oh, sorry, I can put my hand down.
Okay. Okay. All right. Yeah, I guess any other questions, or we end the session here? Yeah, okay, so it seems like there are no other questions, so I guess we can end it. Right, thank you so much, Zhihan, for this amazing presentation. And if people have other questions, they can always reach out to ask them on Discord. So yeah, I think that's pretty much about it for today, and we'll see you next week.